De Rocco that I see already there in the sunny California, Santa Cruz, I guess. And you can start sharing, Will, if you like.
Sure thing. Give me 1 second here. Let's do this over here. All right, so
fantastic. Yeah, it looks good. So perfect. So we are very happy to have Will finishing this day and actually connecting back to Ken Van Tilburg talk. And so Will will tell us how to hunt for axion in the solar basin and probably look at X-ray data from the sun. So please go ahead, Will.
All right, thank you very much. So hello, for those of you who don't know me, my name is William De Rocco, and I'm a postdoc at UC Santa Cruz right now. So today I'm going to be talking about some work that's ongoing, but is very, very close to completion. I think it will be out this month. I'm saying it now, you can hold me to it, that I'm doing with collaborators at Caltech, Perimeter, NYU, and the Flatiron Institute on the topic of hunting for axions in the solar basin. So now, before we get started, I'd like to just give you a rough outline of the talk. I'm going to begin by giving you a lightning fast reminder of the idea behind stellar basins. Then in part one, I'll focus on the specific example of axions in the solar basin and talk about what kind of signal they could produce. And then in part two, I'll discuss the data that we use to constrain this signal and the ultimate results we got out of it. So let's begin with a quick refresher on stellar basins. Usually I'd spend 15 minutes or so explaining the idea behind stellar basins, their formation, timescales, disruption, etc. However, given that Ken gave a great talk and spoke earlier about stellar basins and direct detection, I'm just going to give you a one-slide reminder of the idea. So basically, stars can produce large fluxes of new beyond the standard model particles. I think we can all agree on that. That's definitely been a topic that's been discussed here. Usually, however, BSM searches focus on the escaping flux, or put in another way, the flux of new particles with velocities above the escape velocity of the star. However, a small fraction of the new particles will have velocities that are below the escape velocity of the star. And while this fraction is instantaneously negligible, these particles are trapped on bound orbits and accumulate over the lifetime of the star, forming a stellar basin of slow-moving gravitationally bound particles. And so these were all those beautiful little animations that Ken was showing earlier. So I've tried to indicate this in the diagram here. You can see the bright red line is some fast-moving particle that escapes the star's gravitational attraction. This dark red line is one that becomes trapped and contributes to the basin. And this basin is kind of what I've shown in green here. So that's the whole picture. Hopefully you remember what Ken talked about. Because that's as much as I'm going to say about the generic phenomenon of stellar basins. So let me just restate that takeaway. Stellar basins arise when slow-moving particles trapped on bound orbits accumulate in the gravitational well of the star. Okay, so now let's dig into the meat of this project by focusing on a particular particle, an axion, and a particular star, which is our very own sun. Let me show you the model that we're using for these axions. And I should say that we're really interested in what some people I think would prefer to call axion-like particles, though I'll just use the term axion. The fact that these are axion-like particles really just means that our mass and couplings here are free parameters. So MA, GAEE, and GA gamma gamma, which I'll discuss, we can sort of manipulate as we want, as opposed to being tied to some sort of QCD axion line or something like that. So taking a look at the relevant terms in the Lagrangian here, you'll see that the first term is just a mass for the axion, which is going to end up being near the temperature of the solar core, so about order keV, because this allows a decent fraction to be produced with velocities below the escape velocity. The second term is a coupling to electrons, so GAEE is the coupling to electrons, which is primarily relevant for production. And for masses above about 5 keV, which is we're restricted to due to detector effects that I'll discuss later on, the nominal production process is via the Compton process. The third term is a coupling to photons, which allows the axions to decay to 2 photons. And this is important because this is ultimately, the signal that we're interested in looking for is this decay to 2 photons. I should also note, though, that it allows axions to be produced by Primakov as well in regions of parameter space where, for example, we dial GAEE very, very low. So the electron coupling is negligible. That way you get production via Primakov and then decay via that operator as well. So having been produced, the axions will linger in the basin for roughly the inverse of their decay rate, then decay to 2 photons. And this signal, this decay to 2 photons, this is what we're ultimately looking for. And so I just want to stress, this is therefore an indirect detection search. In contrast with the direct detection prospects Ken was discussing earlier, where he was talking about xenon 1-ton experiments on Earth, etc. And I know that I think today is nominally not even an indirect detection day, but this is an indirect detection talk to follow up on some of the stellar basin stuff. And so one notable difference about the fact that this is going to be an indirect detection search as opposed to what Ken talked about is that we're actually going to be focused on the region of the basin very, very near the sun. Not the region that extends all the way out to Earth that you'd be able to pick up with xenon 1-ton or something like that. So let's talk about what the signal from these decays actually looks like. The energy spectrum is very simple. Since the axions are trapped in the basin, they necessarily have very low velocities. That's how they got trapped in the first place. So they effectively look like they're decaying at rest. And as a result, each photon gets about half of the axion mass. We're interested in axions on the KeV scale. As I said, this is the temperature of the solar core. So this signal really just manifests as an X-ray line with order KeV energy. The angular dependence of the signal is slightly more interesting and exhibits some characteristic features, one of which is a doubling at the solar limb. And when I say solar limb, I just mean the edge of the sun. When you're looking at the sun, the edge of the sun. This is because our observable, the X-ray flux from these photon decays, is ultimately an integrated line of sight. So in other words, we're necessarily summing up the contribution from all the photons from the basin of decays that are propagating along this line, as I've indicated in this figure. Everything that's happening here propagates here to our eye. This signal doubles at the solar limb for the reason that I've tried to indicate here, which is that before you hit the solar limb, you're only integrating over the decays taking place in front of the sun because the sun is opaque. Beyond the solar limb, though, you start integrating both over this region and this region, where previously you weren't integrating over this because, again, photons don't get through the sun. So you can see that that's sort of the reason why as you tilt up towards the solar limb, you get that sort of sudden doubling effect there. So I can show you the angular dependence of the signal, normalized to 1 at the solar center. And that twofold jump at the red line is due to the doubling at the solar limb that I just mentioned. There's also the characteristic 1/r⁴ fall off that Ken talked about in his talk. But in broad strokes, you can see that the spatial signal varies on the scale of arc minutes in a characteristic way. So in summary, we're looking for a narrow line of order KeV energy with spatial variations on the scale of arc minutes or so. And that concludes our discussion of the model and the associated signal. So to summarize, KeV scale axions can accumulate near the sun before ultimately decaying to photons. Our signal is the X-ray line associated with these decays. We're looking for those photons from the decays in the basin. So let's now move on to the final part of the talk, in which I'll describe the data set we used and the constraints on axion couplings that we were able to place. So what can actually detect this signal? I've talked to you about the signal. I've told you what we're looking for. What can we actually use to look for it? Well, given that the photons are in the KeV energy range, we're naturally led to X-ray telescopes, and more specifically, NuSTAR, which is an orbital X-ray telescope that has been in operation for 9 years now. It's a good choice for our search, not only because, as I will mention in a bit, it actually has data, but also because it has an energy range of 3 to 78 keV and roughly 100 EV resolution in energy, as well as 0.3 arc minute angular resolution. So this really makes it uniquely suited to discerning the axion signal. I would, however, like to say that there are a few caveats. So note first that energy range cuts off at about 3 keV, below which new star is entirely uncalibrated. So the lowest axion mass that we can probe is roughly 6 keV. This harkens back to what I was saying earlier about Compton really being dominant above that. Additionally, detector effects broaden any line signal to of order 200 eV, which completely dominates any sort of theoretical broadening from, the axion velocity distribution, Doppler broadening, that sort of thing. It gets washed out in the detector. And finally, one of the more thorny issues is NuSTAR was not designed to point towards the sun. It's a pointing telescope ultimately, or that was its design, to look at distant point sources. So for it to look at the sun, it has to operate in a mode where the absolute pointing uncertainty can actually vary by 2 arc minutes for different combinations of the star trackers that it used to orient itself. And this is just due to the fact that it has to blind one of its star trackers, because that star tracker, that camera, is pointed right at the sun and would get totally burnt out. So it has less information about its orientation, and it means that you have to look at a single combination of star trackers in order to maintain a relative 0.3 arc minute angular resolution that we would need to pull out the angular dependence of our signal. So that cuts down the data a little bit. Even having said all of that, NuSTAR is pretty well suited to this search. So it's exciting that it's up there and that it has data. There's an additional advantage of NuSTAR as well, which is that it's got pretty well characterized backgrounds, which have been studied for 9 years now. So thanks to this, we have a very good understanding of the dominant backgrounds in our energy range of interest, which is roughly 3 to 20 keV photon energies, corresponding to 6 to 40 keV mass axions. Above that, so below that, it's uncalibrated, as I said. Above that, Boltzmann suppression on production just totally kills you. So that green region here is really what we care about. The dominant contribution to the flux of energies above 3 keV is surprisingly not actually from the sun itself. The sun is fairly quiet at those high energies, but rather from the cosmic X-ray background photons, which are leaking in around the detector. So not even ones that have been focused in towards the detector, but ones that are leaking in around and hitting it. Luckily, NuSTAR collaboration has spent extensive time modeling this and characterizing it. And you can see this background here is labeled as aperture. So this well-modeled background affords us several different methodologies that we can ultimately use to analyze the data. And yes, beyond the good energy resolution, the good angular resolution, the well-studied backgrounds, as I've said, NuSTAR actually has data. So NuSTAR performed a set of quiescent solar limb wells in September 2020, which is where we draw our data from. It's actually, to me, fairly exciting that we have this data, because there is surprisingly little X-ray data of the quiescent sun for sort of what might be an obvious reason, which is that solar physicists generally care about an exciting sun with flares and coronal mass ejections and all these sorts of things, and not so much about a very boring, quiet sun, which is mainly used for calibration. So this is sort of a unique data set in that it's very clean and free of flares. So for the reasons that I had to mention previously, we ultimately considered the longest continuous combination of star trackers that appeared in the data in order to ensure our high angular resolution. And we selected an orbit for which the live time was not appreciably diminished by crossing the South Atlantic anomaly, which, to clarify, is a region of high energy particles that are trapped above the South Atlantic. And as satellites pass through, they have to shut off during that period, and so you get some appreciable downtime. And so that's how we selected our data. Now, given this data, we ultimately want to set limits on the axion couplings. So we chose to compare 3 different limit setting methodologies, actually, each of which had their own respective pros and cons. And I really won't have time to get into each of these, but I've made a little table to give you a sense of the trade-off between them. And I'll try just now to describe them in no more than a few sentences. So the first is this sort of naive Poisson limit, which I'm sure most of you are familiar with. The idea here is just to ask, okay, given the total number of counts you observe in your data, how large can the signal be before it would conflict with the data? And the answer is ultimately pretty simple. It's kind of as you guess. It's roughly the number of counts you observed. But note that this doesn't require a background model, right? You can do this. You're given data, you have a signal expectation, and you can set the Poisson limit. However, it doesn't use any spectral or spatial information, for example. So we had a spectrum we understood, we had a spatial distribution we understood, and that should in principle allow you to improve this limit somehow. So the next is the CLS method, which might also be familiar to some of you who spent time working on LHC analyses, these sorts of things. Here, what you do is you have to simultaneously fit both a signal model and a background model to determine how large the signal could be before the joint model conflicts with data. Critically, this requires a flexible and robust background model, which isn't always possible to construct. We are lucky enough to have a pretty well-characterized background, but we didn't know that going in. So finally, there is the Yellen method, which is the one that I think the fewest of you will be familiar with. The basic idea here is to look for underdensities in your data set in comparison to the expectation from pure signal, and to use those to set constraints on the signal. Now, critically, this is in general more powerful than Poisson, but also doesn't require a background model like CLS. Unfortunately, here's the issue. Before our work, it had never really even been extended to multidimensional data because it becomes very computationally intensive as the number of dimensions increases. So our 4 dimensions of arrival time, energy, and X and Y position on the sky for each photon was really just barely achievable after a lot of CPU hours and several weeks on a supercluster. So now finally, it's time to show you the results as promised. These are fairly hot off the presses. These are from about a week ago, which is why I think this paper is actually going to come out soon. Since we have a multidimensional parameter space, we have to choose some relation between GA gamma gamma and GA EE in order to show this on your sort of typical mass coupling plot. So we chose the one up here, just as it's an arbitrary slice. There's a full 2-dimensional map as well that I could show at some point, but it's kind of complicated. And so we tie it to some F axion decay constant. And so you can see, for example, here are our bounds. You see that Yellen outperforms Poisson at all masses, which really isn't unexpected. In our case, this improvement was actually fairly marginal, owing to the fact that Yellen, in principle, provides the largest gains in data with sporadic localized features, which our data ultimately didn't have. It was very uniform. But it still demonstrates, the ability to set stronger constraints than Poisson in the presence of an unknown background, if you had no idea what your background model was. Furthermore, the CLS method is stronger than Yellen for our data, suggesting that the uniform background that we modeled, which wouldn't, for example, capture a local microflare, was a very good description of our data. But the real takeaway here, though, is that we are able to constrain parameter space in order of magnitude below current limits from the red giant branch. So that's fairly exciting. And I'd also like to briefly flash up the equivalent plot for an axion, which we've set the electron coupling to 0. Hence, production is done via the Primakov process, as I mentioned. So it's photon production and photon decay. So you're probing only GA gamma gamma here. And so, there's no assumptions on the other couplings. And you can see these constraints end up extending 2 orders of magnitude below existing limits. So that brings me to the end of my talk, but I want to just briefly remind you the key takeaways. Firstly, as I reminded you in my first slide, stellar basins of new particles are a fairly generic phenomenon that can arise when slow-moving particles fail to escape the gravitational attraction of a star. Secondly, I described the potentially observable signature associated with the decays of axions that have become trapped in the basin of our sun. And finally, I showed you that existing data from the New Star Telescope can be used to set new limits on axion couplings via various means, and that these data ultimately constrain axion couplings over an order of magnitude below existing bounds. So with that, I will conclude, and thank you all for taking the time to listen to me.
Thanks a lot, Will, for this very nice and very clear talk. So now it's time for question. And I will start, actually, given that, I have this privilege. So I will start. I actually have a question about the solar activity, right? Because you mentioned this fact that, plasma physicists are not interested to that, but it's not also the fact that quiet period of the sun are not that often, which is the period of the sun, after how many months, let's say, or whatever you expect the quiet period that you were using, for example, and in principle, in general, not how much they look at it, right? In general, how how much does it last, or like?
So I think it really depends on what you define by a quiet period, right? So there's, the full solar activity cycle, which is like an 11-year cycle. And so you have sort of
exactly
in the middle, et cetera. But I mean, that's sort of for global solar activity, right? That's not really what I would consider like a quiescent period. A quiescent period is one you almost only know retroactively. Because it can be sort of stochastic, where sort of individual micro flares are appearing and that sort of thing. So, a quiescent period is one that is basically defined as not having flare events in it. And so you sort of do these long limb dwells, and you look for regions where there doesn't appear to be signs of a lot of solar activity. But I'm not sure that you can sort of slap a, and this is how long we expect it to persist onto it. It might be a better question for a solar physicist.
Okay, thanks, Will. Okay, now Eduardo has a question.
Oh, thanks for the nice talk as usual. So two questions. First of all, for the photon coupling, when you show the bounds for using only the photon coupling, is that coming from a basin or from the basin, or it's coming from the Primakov production, and then you take you take the decay of the axions coming from the sun? Because as Ken has explained, Primakov production has the problem that basically it suppresses low momenta. So
no, this is from the basin. All of that accumulated particles in the basin.
Okay.
Otherwise, Eduardo, I don't think that you have the time to decay. These masses
exactly.
These time are very small. So
it takes forever. It takes it takes forever to decay. So I was a bit confused, because you see that Primakov production is suppressed low momenta. So both cases sounded weird to me. But okay.
I mean, no, but you still produce these, right? And they still accumulate, and you can form the basin.
No, I had another question, but I can.
Yeah, please go ahead.
No, the other question was so apparently these measurements are very, very much better than what I expected, because I thought that that even with a quiet sun, I expected a lot of noise due to solar activity, even when the sun is very quiet. So
you should keep in mind, right, that solar activity, all of that peaks. Well, it's a falling exponential, really. And so above about 3 keV, the sun is pretty quiet, honestly, most of the time. If you were to push below that, I mean, you can look at that background plot again, right? And you can see that. Let me see if I can go to the background plot pretty quickly. So if you look here, for example, right, this is the solar activity, right?
Wait, give me a second. Yes.
Yeah, so here's the solar activity, right? Which is not the dominant background for these high energies. It is really from cosmic X-ray backgrounds. Now, below 3 keV or so, this thing rapidly increases. So if you try to push even an order one number down this way, you start running into a lot of solar activity, and it becomes very, very complicated, which is why we were considering initially, since we didn't know this before we brought Brian Greffenstedt on, who's like a solar physicist who's working on NuSTAR. We were trying to think about ways of doing this in a totally background agnostic way, which brought us to the Yellen model, for the Yellen limit setting procedure. But
and the reason is that all this stuff is always like kind of thermal emission, right? So it will peaks around right at lower frequency, like this is what you're saying, like like keV, like really keV. So when you go to this larger, like already 10, 20 keV, you're already kind of exponentially suppressing the active. I see.
I think but in any case, so what you're saying is that like you're looking at above 5 keV or so.
Well, I mean, sure, we're looking above 3 keV, where NuSTAR.
Yeah.
So no, I was just wondering. What if one could get. No, it's so small, the neutrino flux. I was just thinking about radiative decay from neutrinos, but but the flux is too small there, because usually one looks at larger flux, so you have to go to MAB and then perhaps I mean I think that Georg did it like 40 years ago or something like this, but yeah, no, probably you cannot get anything better from this.
Okay, there, because otherwise I don't know if you're running out of time. If there are any other question, of course you can raise your hand still, like while Eduardo and Will are discussing. And okay, actually don't see other hands, other raised hands. So I think that we can close this the recording here.